Now, the first question here, I just wanted to let me just show you what was expected of you in order to work out through this paper. The first question you were asked to state which of the following is the SI unit of stress. Remember, stress is given by the formula. Stress is given by the formula. Let me just show you. Stress is equals to force over area, and force is Newton, area is meter square. So the unit is Newton per meter square, and that is the option D that we have there. Which of the table contains only vector quantities? And you need to remember that vector quantities are those quantities which have both direction and magnitude and direction. So the best answer there is acceleration, momentum, and weight, which is option A. Going forward, there is question here. Next question, we are told that the spring is stretched by applying a force of 3.0 newtons. Elastic strain energy stored by the spring is 0.04 joules. And remember, we are supposed to state the expression which gives the extension in meters. But remember, for you to work out elastic potential energy in a stretched material, you're going to use the formula E equals to a half Fx. And the formula is energy stored is a half Fx, or another formula you can use is A is equals to a half Ke squared. So, but for this case, we're going to make this formula here, and if you work it out, the answer should be A. Now, here we are told that a cyclist moves along a horizontal road at a constant speed. She then moves at the same speed uphill at a constant gradient. So, something that you need to remember is that moving at a horizontal road, the power should be low, right? The power should be low, and moving a steep area at a constant velocity, the power should be high because now it's moving uphill. So the answer there is E. Move to a student drops a table tennis ball and the ball fell for a time t and a velocity v just before it hits the ground. The student used the equation of motion to calculate t and v. This equation ignore air resistance. Which row of the table shows how the actual value of compared with the student's calculated value for t and v? So if it was actual, remember there could be air resistance, so it would have taken longer time in order the object to land on the ground. So the greater t should be greater than the calculated value, and also v will be less than the calculated value because of the air resistance. There is a bird that is resting at this point. Remember, it's exerting a weight down, but having the tension of this spring acting that direction, it has a vertical component. Also, since we are having another force on this other end, also we have another vertical component. So when we are going to say, because this is tension, we can be able to say we need the vertical component of that tension force, and this angle here is 80 degrees. This side is adjacent to the hypotenuse t. Then we can be able to say, to work out the vertical component is going to be t cos 80 degrees. But since there are two of them, there is another one here. We're going to say 2t cos theta, which is 180. Theta is 180. Then this should be equal. The total vertical component should add up. The one of it will be t cos theta. Another one will be t cos theta. Then the two of them will be 2 cos theta. Because the body is at equilibrium, then it means that downward force should be equal to upward forces. So that's why I equated this expression that I am having at that point. Then if you divide both sides by 2 cos theta, and the best answer is going to be C in this case. The gradient of the graph represents stiffness, and you can see this one represent 1 over k. So that is C is the correct answer for that. We are told a solid of a cube weight W is made from a material with a density P. So you need to remember that weight is equals to mg. Then the way we were to get the mass is weight divided by gravity. And then remember the formula, density equals to mass divided by velocity. Remember density equals to mass over volume, and meaning that from here we can be able to volume using the formula V equals to mass over density. But our density, our mass was weight over g, so this volume is going to reduce this. But since a cube has all sides equal, then we can say s times s times s is going to give us the volume. Then one side will be the cube root of w over density times gravity, and the correct answer is C as shown there. Which of the following statements is correct? We can say that A is saying P has the greater breaking stress. No, Q has greater breaking stress. You can see is here, and you can see it's higher than this one here. This is the breaking stress. P has a greater breaking strain. You can see Q has a larger strain here compared to P. So that is not true. P has a greater yield stress. Yeah, that is true. Yield stress is greater. You can see it. This one is less. So that is the correct answer. P has a lower Young's modulus. Remember, Young's modulus is obtained from the gradient of the graph. And then we can see Q is less steep than P. So P is having a higher Young's modulus because of the graph being steeper. So D is also not correct. Now, something you need to appreciate is that the area under acceleration time graph is representing change in velocity, change in velocity. And in that case, meaning that if x is the change in velocity, so, and assuming that this is starting from 0, you can see there, we can be able to come up with a velocity time graph. Area under the graph represent the change in velocity. Have already opined that. And then we can be able to come with a velocity time graph. Change in velocity for this case will be 0x, and in the time t. So if we want to work out the total distance covered, we're going to work out the area under this graph. So meaning that is going to be a half base times height, which is a half times x times t. And if you work it out, it's going to be xt over 2. Because this is a triangle, so we're going to say a half base times height. And this is t times v, which is our height. Our height is x, right? Our height is x. And the x, we got it from here, change in velocity. Yeah. So if this is 0, initial velocity was 0, for us to have a change in velocity, we must have our x at this point. So if we subtract, we have the same change in velocity. But the time taken is t. So to work out the distance is equals to area under the graph. Area under the graph. So you can see working out the area of this graph is based on height, which is going to translate to this. Now, when the student is loading and increasing the force, something that you need to remember is that area under the graph represent the work done. And area under this section also here is going to represent the work, the energy that is given out. Area that includes everything here from the top graph to the everything down here represent the work done to stretch that material. But when it's unloaded, this area that I've shaded red represent the energy that is given out. But you see now there is some energy that is wasted when a rubber band, when a rubber band is being stretched, there's some energy that is wasted in form of heat. And that is actually the energy that is in this region that I've numbered here. So if we are to state how the graph shows that the rubber band deforms elastically, elastic deformation is when a material um, returns to the original length and shape when the force is removed. So the way we can be able to note that is that after all the forces have been removed, the material went back to the original length. There is no extension. The extension now is zero, which indicates that the material returned to the original shape. That is elastic deformation. But plastic deformation, if it was plastic deformation, this maybe could have gone and then it ends here. Yeah. So meaning there could have been some extension this way, meaning that the material stretched plastically. Now, let's see the response I gave. When the force is removed, the rubber band returns to the original length. That's shown by the zero extension that we are having at that point. Now, the work done on the rubber band has F increased is greater than the work done by the rubber band as it was decreased. There is a difference in this value because of the heating and the thermal energy transfer that takes place. I've already opined that. Determine the energy that caused heating as F was increased and then decreased to zero. So the first thing that you need to do, you can not be able to use direct method in order to find the area of this section. So the thing that you're going to do, you're going to use square counting technique. So you're going to count full squares, complete squares, and to count the complete squares, and you can see here this is a full complete square. 1, 2, 3, 4, 5, 6, 7. Then we have 7 complete squares. Incomplete squares are 21. The way I counted, I got 21. So the total number of squares that we are going to have in this case, the total number of squares we are going to have here, total number of squares is going to be complete square plus a half incomplete. So 7 were the complete one, incomplete were 21. So you have to say times a half times 21. So that becomes 18.5. Now, once you have done that, something else that you need to remember, you are supposed to do is to work out the area of 1 square times the number of squares you have. So area is, this one is 0.5 here, but this one is 0.5 also, but take note of the units that is provided here. You must convert the 0.5 to meters. So you are going to say 0.5 divided by 100 to get 0.005, then times 0.5 force here, because you want to know what's the work done in 1 square, so that we can be able to multiply by the answer we get by 18.5 squares that we got. 1 square has how many joules of energy? Newton meter. How many joules of energy? This is going to be 0.5 times 0.0005. So if you work it out, 0.0025, 0.0025, and joules for 1 square, then times this value that we have. And that is basically what I've done. That's what I've done below here, so that we can be able to, we could get this value at that. And also in this question, we are given a tube, and this tube has some air somewhere inside here. So when this thing is squeezed, when you press it, more water will get into the tube. And the moment there is more water in the tube, then this tube or this Cartesian diver is going to have a greater weight, which is going to be more than the upthrust. So when weight is greater than the upthrust, this Cartesian diver is going to sink down because the resultant forces will be acting downward. So explaining why the diver accelerates downward is because when more water is forced into the tube, the weight of the tube increases. So the weight is greater than upthrust. Hence, Cartesian diver accelerates downward because there is a resultant that acts downwards. Tricky is that if you look at this slide here, it's having different slopes. Here is steeper, this is less steeper, this is steeper. So meaning acceleration is not going to be constant as this child is going to be swinging down here. So the acceleration of the child is going to differ depending on the point and the position the child is swinging. So now we are going to say that the reason as to why the equation of motion cannot be used to determine the speed at the bottom, yeah, maximum speed of the child at the bottom here is because as the child is swinging, the slide is having different steepness. So the acceleration of the child is not going to be constant. So it will be varying. And in that way, we cannot be able to apply the equations of motion because the equation of motion only apply under constant acceleration. The next bit, we are told to determine the maximum speed of the child. And to do that, we are going to use the concept of conservation, the law of conservation of energy. Energy can be converted from one form to another, from potential energy to kinetic energy. And potential energy is mgh is equals to a half mv squared. Then you can see even without being told, you're able to cancel this. And rearranging this, we're going to get this. And we're going to get our answer, and this can cancel out rearranging. We're going to get, and here the velocity vy and vx is going to same. This because the final maximum speed, the final speed down here does depend on the, so which will what will happen, that they are going to down here at the same maximum speed. Vx should, remember they are having the same gp, because they are at the same height. Both of them have this. So for that, we can Bx will be y because 15. We are told a student in a small ball bearing falling through a fluid to determine the viscosity of the fluid. Then we were supposed to state the condition needed to apply. One of the conditions is that the object should be moving fast. It's gonna cause turbulent flow, and also the flow in this case must be laminar. It should not be turbulent. So we are going to try as possible try to work out this question and find whether the value of eta that we're going to have there is going to. Now, remember the volume of a sphere is given by 4 pi r cubed. And I applied this because this was given in millimeters, so you have to multiply by 10 raised to negative 3 in order to convert it to meters. So don't forget that during your exam. So working out the volume, you get 5.096 times 10 raised to power negative 8. That's the volume of this sphere, right? Ball bearing, right? and the volume of the ball bearing will displace the same volume of the liquid. So the volume of the liquid displaced will be that. Mass of the liquid can be given by density times volume, and then we can be able to get the mass as that. Then we can now work out the weight of the liquid displaced as 6.3 times 10 raised power negative 4 newtons. And this represents the upthrust force, right? This weight of the liquid, it also represents the upthrust force, because from Archimedes' principle, we say that upthrust is equal to the weight of the liquid displaced. But remember, uh, upthrust plus drag force is equal to the weight. But if we take weight upthrust on this other side, it becomes minus. Then I want to use the weight that was given so that we can be able to work out the drag force. And our drag force is equivalent to 3.37 times 10 raised to power negative what? Negative 3 here. Negative 3 that we have at that point. So remember, drag force can be worked out using this formula. And then we are having we are having 6 pi eta radius in meters, and then this is the terminal velocity, of course. So we try to make eta the subject of the formula, work it out, and check whether is it going to be same as this value that we have at this point. So if it's going to be the same, then we can say the liquid used was glycerol. So working out this and substituting correctly, we're remembering that the radius was given in millimeters, so you have to convert it. Then it means I'm getting 0.94 a second, and that is Pascal second. So which means approximately 93 Pascal second, and that means we can be able to say the liquid was. That's what you are supposed to do. And we are having a skitter here, and the skitter is just moving that direction to collide with the ball is moving to collide with the skitter. And we were supposed to work out acceleration. We identified this point to be 15, and we identified 8. We identified this point to be 8 or 2.85. 2.85. But what I need to remind you, this one is very one you have to say it's times 10 raised power negative 3. You have to interrogate this. Huh? So if you work out the acceleration, you are going to get 86.4 meters per second square. The next question, explain how Newton's second law and third law of motion apply to the ball and the skitter during the collision. Now, let me just show you here. When this ball collides with the skitter, it exerts a force, and this force is going to create a resultant force for the skitter, and this skitter is going to do what? Is going to experience a force to the left, and it's going to accelerate to the left, right? But since a skitter is since the ball has exerted a force on the skitter also will exert a force of equal magnitude but in opposite direction. So that force that is acting this direction will make this ball to decelerate, right? According to Newton's second law. Newton's first law in connection with this is when the ball exerts a force to the skitter, then the skitter exerts an equal but opposite force in the opposite direction. So how are we going to link this? We're going to say When the ball collides with the mosquito, it exerts a force. When the ball collides with the mosquito, it exerts a force on the mosquito. And the mosquito also exerts an equal force, but in opposite direction, according to Newton's third law of motion. So the resultant force decreases and the ball accelerates. The ball decelerates. The ball will decelerate because there will be a force that is trying to oppose the motion of the ball. But for the mosquito resultant force will be acting to the left. Remember, the mosquito was at rest when the ball was accelerating towards it. There was no force. But since there is a force exerted on it by the mosquito, it's going to accelerate to the left according to Newton's second law of motion. So that is exactly what you are supposed to state in this question. Now, for us to determine the mass of the ball, remember the ball, we can let it to have a mass b, and initial velocity of the ball was given as 7.2. But the mass of the mosquito was 1.4, but initial velocity of the mosquito was 0 because initially it was at rest. When they collided, the velocity of the ball became 1.6, and the mosquito moved at a speed of 3.1. So we're using the law of conservation of in momentum. We're using the law of conservation of momentum, that momentum before collision is equal to momentum after collision. Now, if you work it out here, you're going to get your answer, approximately 0.775. A student determined the Young's modulus of a material in a form of a wire. The student used a micrometer screw gauge to determine the diameter of the wire, and we are supposed to describe how the student should check the wire's uniform and check what whether the wire has circular cross section. Remember, for a circular cross section, the diameter should be the same throughout. So the student should measure the diameter in several different positions along the wire and put the micrometer in different orientations so that you can be able to note whether the diameter is the same throughout. To explain other safety precautions, because that wire can snap and break and end up just getting into somebody's eye. So in that case, we really tried to ensure we are wearing spectacles or goggles to protect the eyes. The wire may snap and hit somebody. Explain why you should measure using a vernier scale. The vernier scale has a better resolution, so there is a small percentage uncertainty vernier scale, and this minimizes errors. Now, in this question, you are supposed to one of the point in anywhere in this straight section of the graph. You identify. You could even have come and identify at any point. You could even say here, you check which value at this point, and you just draw a straight line there, and then you can be able to identify extension, and you identify the corresponding value of the force. So using that, you could now go down here, like for instance, because we were to determine or deduce the material that was on this wire. So whether it was brass, aluminum, or steel, you see what I did. I identified the extension and I also identified the force from the graph. Then I used the information provided here to determine the Young's modulus, because remember, Young's modulus is constant. It doesn't for if as long as the material is the same material, the Young's modulus remains the same. So remember, Young's modulus is stress over strain, but stress is force over area. So I went ahead and worked out the area of this figure here, area of the wire. That is the cross-section area of the wire. I worked it out, and I used the diameter that was provided here. So whenever you're working out that area, remember that you have to convert these millimeters to meters by dividing by 1,000. Then also you have to divide this by 2, so that it's radius, because it was given as diameter, and that's why you see I divided by 2,000. 1,000 to convert to meters, then 2 also is to divide it to become the radius. So that's why you see a 2,000 here. I multiplied 2 times 1,000 that I used to convert this to meters, and I worked out the area. So I went ahead and worked out stress, which I got here. And then remember, strain is extension over, my extension was this, and my extension was in centimeters, so I had to convert to meters and then divide by the original. So when I worked out my value, I got it 1114 gigapascals. And remember, giga is the same as 10 raised to power 9. So this value I got here, I divided by 10 power 9, so that it became such a beautiful value here. But if you can be able to compare the values, this, it was close to this, and then I concluded the material that was there was brass. This is also another interesting question that was asked, but the first question was quite straightforward. To state the condition needed for the door to be at equilibrium, we say that at equilibrium, the resultant force in any direction should be 0 and no resultant moment about any point. So resultant moment about any point is 0. So you could be able to say it like that. To, to define the center of gravity, this is the point at which all the weight of an object is considered to act, and then you earn your marks. The diagram shows the forces, the force acting on the door, and then the mass of the door, we are told, is 14.4 kgs. Then you are told the weight of the door causes the moment. Then show that the horizontal component of the hinge of inch Y on the door is about 14. So something that you need to remember, the weight of the object will be acting somewhere at the middle here, at the middle. And remember, the length L was given as 1.6 meters. This length was given as 0.5. So this distance here is 0.425, because you take 0.85 divided by 2, you get 425. Now, once you have identified that, and I'm going to work out this question by assuming that. Now, something that I want you to remember, if this door is resting on this hinge, and this is Y, and this is X. So something I want you to understand, this hinge is providing a horizontal, right? So that if by any chance this is rotating about X, this is rotating about X like that, the force F is preventing it from experiencing a clockwise moment. So the hinge is protecting it from going in the clockwise direction. So which means that we can take our moments about X. We'll take our moments about X, and we're going to work out the weight of the door, so that we are going to use it as our force, because the weight acts here, it's going to be acting downward. So about this pivot, we are going to have a perpendicular distance. Remember, the distance, a moment is force times perpendicular distance. The force we shall be having for the clockwise moment is going to be a weight pulling this door to swing this direction, right? But the distance we're going to use is the perpendicular distance from the pivot, to the line of action of the force. This is the line of action of, so the distance is still 0.425 for the weight here. And this is going to give us the clockwise moment. But this force, which is F of y in the horizontal direction, will be pushing this door as though it will give it anti-clockwise moment. So if you are pushing in this direction, you are giving anti-clockwise moment. But the distance we shall use is the distance from x to y. So we are going to say clockwise moment equals to anti-clockwise moment. And we're going to say the weight of the door is 141.26 times 0.425. And I've told you why. Remember, a distance you use is distance from the line of action of the force. This is the line of action of weight. And to the our pivot is x at that point. So the distance we're using is this, which is a half of 0.85. So working it out, and the force Fy in the horizontal direction, Fy in the horizontal direction, is going to be equivalent to what? Equivalent to 37.5, which is now we have already gotten this force here, and we can be able to say this force here is the same force that can be transferred at this point, and this is going to be what? 37.5 newton. Yeah, but we are told that the hinges, each hinge of the door is equal a half the weight of the door. So meaning the vertical force that will be acting on hinge Y will be a half the weight of the door. So that force that will be acting vertically from hinge Y upward will be 70.63. But this force already I've told you is the one that we have worked out from the previous section. So when I decided to draw and represent this, I moved this force up here so that I can have a triangle with my force of 37.5 here, and the angle theta is here, and 70.63 is acting upward. So we can be able to use that information so to work F and also to work theta. So to work theta, we're going to use opposite over adjacent, which is going to be tan theta is equal to 37.5 over 70.63, and that gave us 27.97, which is 80 degrees. Using opposite over adjacent, then you find the tan in. But now, remember, we have the angle. We can be able to say, if you have F and this side here is opposite, you can say F sine of 27.97 is equal to the opposite side, equals to the opposite side that we are having here. So I related that in order to work out the horizontal component of the force here. So which gave us 80 newtons, 80 newtons. And considering the moments about x, in order to respond to this, I said clockwise moment due to weight remains constant because the weight of the door remains constant even as L is reduced or is made smaller. And then since the vertical component of the force remains the same, also remains the same, the force F must increase, and since the vertical component remains the same, then theta also should increase. If you found value from this particular video, consider subscribing so that a tutorial you'll be notified. See you in the next video.